Hi everyone, welcome back to Dave's Math channel. This is my 7th lesson in my subseries on derivatives of my series on first year calculus. And today I'm going to talk about how to differentiate rational functions. It turns out that now that we, with all the rules we have so far for differentiation, we can differentiate arbitrary rational functions. And here's an example on this slide, which I will do later. Anyway, let's begin. So first I have to tell you what a rational function is. It's pretty simple, actually. A rational function is just a ratio of two polynomials, two univariate polynomials. We're doing all univariate. So we can write a f rational function as f of x equals u of x over v of x, where u of x and v of x are both arbitrary univariate polynomials. Anyway, that's what a rational function is. And like I said, since we know how to differentiate polynomials, I went over that in the last lesson. We also know how to differentiate quotients. We know how to differentiate all rational functions. So nothing really more to be said about that. Let's just jump in and do some examples. So here's the first example. This is a pretty simple example. So let's consider the rational function f of x equals x squared minus 1 over x squared plus 1. Well, here we can let u of x as the numerator equal x squared minus 1, and we let v of x as the denominator equal x squared plus 1. And now we just use the quotient rule. So we write that down. F prime of x, if you remember the quotient rule, it's equal to it's kind of this messy expression here. V of x times u prime of x minus u of x times v prime of x in the numerator, and v of x quantity squared in the denominator. Now we just plug everything in. And so v of x is x squared plus 1. U prime of x, that's the derivative of x squared minus 1. That's 2x. And now we subtract the product u of x, that's x squared minus 1, times derivative of v of x, which is again 2x. So that's what we have in the numerator. And we divide the whole thing by v of x squared, which is x squared plus 1 quantity squared. And now we just have to simplify the numerator. So notice that 2x factors out of the numerator. It just happened in this case that both the numerator and denominator have the same derivative, so we can factor it out. So we had 2x times what's left over is x squared plus 1 minus, if you like, the polynomial x squared minus 1, but we can also write that as minus x squared plus 1. Notice the x squareds cancel here, and you're just left with 2 in the second term. So we're going to get 4x in the numerator and x squared plus 1 quantity squared in the denominator. That was a pretty easy example. But they get harder. And let's look at a more difficult example. Here I have a function f of x equals 3x squared minus x plus 4 over x squared minus 5x plus 9. So let's do this one. So again, we do the same thing. We let u of x be the numerator, which is 3x squared minus x plus 4. We let v of x be the denominator, which is x squared minus 5x plus 9. And now we just use the formula again, the quotient rule, which I'm not going to state. But if you work out the numerator without simplification, you just get this quantity in the second line, x squared minus 5x plus 9 times 6x minus 1 minus the product 3x squared minus x plus 4 times 2x minus 5. Well, now you got to do a lot of multiplications, but I think you guys know how to do this. I mean, this is kind of just generalized FOIL. So you have to collect like terms. That's kind of the trick here. And you're going to get an x cubed term for the product of the first two terms. The highest power of x is x cubed, and I think you can see that you're going to get 6x cubed. That's just the product of the leading terms in each polynomial. And then to get the x squared term, we actually have to add two terms. We're adding minus 1 and minus 5 times 6, which is minus 30. That gives you minus 31. So you get minus 31x squared. And then for the linear term, you get minus 5 times minus 1, that's plus 5 plus 54, so that's going to give you 59, so you're going to get 59x. And finally, the last terms is 9 times minus 1, so that's just minus 9. And now we have to kind of play the same game with the second product. This is probably the hardest part of the problem, by the way, because you're having to multiply out a lot of terms, and it's easy to make a mistake too. You have to check your work when you're done. So anyway, for the cubic term here, we get 3x squared times 2x. That's 6x cubed. And then for the quadratic term, we get 3x squared times minus 5. That's minus 15x squared. And then you're going to get minus x times 2x. That's minus 2x squared. When you collect those, you get minus 17x squared. And then for the linear terms, you get minus x times minus 5. That's plus 5x. And then you're going to get plus 4 times 2x. That's plus 8x. That's going to give you plus 13x. And finally, the last terms give you minus 20. And I put the second polynomial in parentheses. It's easy to make sign errors when you do this. So that's when you're subtracting something. I like to put the thing you're subtracting in parentheses. But then when you work everything out, I'm not going to bother with the math here. But the numerator turns out to be minus 14x squared plus 46x minus 11. Notice that the cubic terms cancel, so you're left with a quadratic term in the numerator, a quadratic polynomial in the numerator. And then the denominator is just what it was before, x squared minus 5x plus 9 quantity squared. So that's a harder example, but that's how you do that. And I think I'm going to finish with the example that I showed on the introductory slide. So this was, I think actually this one's a little bit easier than the last one. So now we have f of x equals x squared plus x minus 2 divided by x cubed plus 6. And let's calculate the derivative of that. So x prime of x, again, you use the quotient rule. V of x u prime of x minus u of x v prime of x, or v of x quantity squared. And so v of x is x squared plus 6. U prime of x is 2x plus 1. That's your first product, and now you're subtracting the product x squared plus x minus 2. That's u of x, and you're multiplying that by v prime of x, which is 3x squared. And your denominator is x cubed plus 6 quantity squared. That's v of x squared. And now we simplify things. This one's not so bad because now we have fewer terms, so you can use FOIL on this first product. And you get 2x fourth plus x cubed plus 12x plus 6. That's pretty easy to see. You don't even have to collect terms here. And then for the last one, you get, you're subtracting 3x fourth plus 3x cubed minus 6x squared. Both of these are pretty easy to calculate. I probably should have made this example too, because I think this one's a lot easier than the last one. But anyway, so finally you just collect terms. So you're going to get minus x to the fourth minus 2x cubed plus 6x squared plus 12x plus 6 in the numerator, and you get x cubed plus 6 quantity squared in the denominator. And I believe this is the same thing they show on the introductory slide. Let's just look at it. Yeah, it looks the same. So good, we did it right. Okay, so that concludes my video. That's how to differentiate arbitrary rational functions using the quotient rule and the rule for differentiating polynomials. And that concludes today's lesson. Thank you for watching. Long live math, and I'll see you guys next time. Bye.